What if I told you the universe is holding its breath just for us? Think about it. The numbers that shape reality, the constants that govern everything from the tiniest atom to the vast expanse of galaxies, are balanced on a knife's edge. Change them by even a fraction, and the entire cosmic symphony falls apart. Gravity slightly stronger, stars burn out too fast, the speed of light a bit slower. Chemistry itself would unravel. This isn't a hypothetical scenario, it's the startling reality we live in. The universe's constants aren't just random numbers, they're precision-tuned, as if someone or something set them exactly right to make life possible. And that raises a question so profound it sends shivers down the spine. Why? We're not talking about minor coincidences here. Take the fine structure constant, a number that dictates how atoms hold together. If it were just 4% different, carbon, the building block of life, couldn't even form. Or consider the cosmological constant, which controls the expansion of the universe. A little too high and matter would never clump into galaxies. A little too low and everything would collapse before life had a chance to begin. These aren't just abstract ideas, they're the invisible threads stitching reality into a fabric that allows us to exist. It's as if the universe itself whispered, "Here, this is how it has to be." So what does it all mean? Are we just lucky, or is there something deeper at play? Some scientists call it the Goldilocks principle, the idea that our universe isn't too hot, too cold, but just right for life. Others wonder if we're seeing hints of a grander design, or even evidence of multiple universes, each with its own set of rules. Whatever the answer, one thing's certain: the more we learn, the more mysterious it becomes. This isn't just a story about numbers and equations. It's a story about us, about why we're here, in this particular universe, at this particular moment, able to ask these questions at all. And that's a mystery worth exploring together. So let's dive in, because the truth might be stranger than anything we've ever imagined. The fine-tuning problem isn't just a quirk of physics, it's a cosmic puzzle that challenges everything we think we know about existence. Picture a vast control panel with dials representing the universe's constants. Each one is set to an unimaginably precise value. Turn the dial for gravity even a hair to the left, and stars would collapse into black holes before planets could form. Nudge the strength of the nuclear force slightly to the right, and hydrogen would fuse too violently, leaving no stable elements for life. It's not just one or two dials that need perfect alignment. Dozens of them must be exactly where they are, or the whole system falls apart. Now here's where it gets even stranger. The odds of this happening by chance are so astronomically low. It's like flipping a coin and getting heads 1,000,000 times in a row. Statistically, it shouldn't happen, and yet here we are in a universe where every constant, every force, every law of physics seems to conspire in perfect harmony to make life possible. Some scientists argue this points to something far bigger than luck. Maybe the universe isn't random at all. Maybe there's a deeper principle at work, a hidden logic we're only beginning to glimpse. One compelling theory is the multiverse. Imagine countless universes, each with its own random set of constants. Most of them would be barren, chaotic, or instantly collapse. But in a handful, maybe just one, the numbers line up perfectly. We just happen to live in that one. It's a cosmic version of the lottery. With enough tries, even the most improbable outcome becomes inevitable. But not everyone finds this satisfying. After all, if there are infinite universes, why do we perceive this one as so finely tuned? Could there be another explanation, something beyond pure chance or infinite possibilities? Then there's the philosophical angle. Some thinkers suggest the fine-tuning points to intentionality, as if the universe was meant to produce life. It's not proof of a creator, but it raises profound questions about purpose and design. Even the most hard-nosed physicists admit the fine-tuning problem is unsettling. It's as if the universe knew we were coming, setting the stage billions of years in advance. Whether you see that as poetry or a scientific challenge, one thing's clear: the fine-tuning problem isn't going away. It's a clue, one that might lead us closer to understanding not just how the universe works, but why it works this way at all. The cosmological constant is one of the most tantalizing mysteries in modern physics, a single number that holds the fate of the entire universe in its grasp. Think of it as the universe's throttle, controlling how fast space itself stretches. If this constant were even slightly stronger, the expansion of the cosmos would accelerate so violently that galaxies would never form, scattering matter into a thin, lifeless haze. But if it were just a fraction weaker, gravity would win out, pulling everything back into a catastrophic collapse long before stars or planets could ever take shape. And yet, against all odds, the value we observe is balanced on a razor's edge, so precise it defies belief. This isn't just a lucky break. The cosmological constant is fine-tuned to an astonishing degree, around 1 part in 10 to the power of 120. To put that in perspective, it's like hitting a bullseye on a dartboard the size of the observable universe, blindfolded on your first try. The odds are so vanishingly small that even some of the most skeptical scientists pause when confronted with the numbers. How could something this precise happen by accident? One camp argues this points to something beyond pure chance, a hint of deeper order. Maybe the universe isn't random at all. Maybe the cosmological constant is what it is because it has to be, governed by some undiscovered law that locks it into place. Others take a different approach, suggesting that our universe is just one of countless others, each with its own randomly set constants. In most of them, the numbers don't work out, but in ours they do, and here we are to notice it. It's a compelling idea, but it raises its own questions. If there are infinite universes, why does this one feel so meticulously arranged? Then there's the possibility that we're missing something fundamental, a hidden symmetry or principle that naturally explains why the cosmological constant is what it is. Some theories, like string theory, propose higher dimensions or unseen forces that could influence these values in ways we don't yet understand. But so far, no one's found the smoking gun. What makes this even more fascinating is that the cosmological constant isn't just a theoretical curiosity. It shapes the destiny of everything. Right now, it's causing the universe to expand faster and faster, pushing galaxies apart until, billions of years from now, the night sky will fade into darkness as distant stars vanish beyond the cosmic horizon. It's a reminder that the very laws allowing us to exist also set the stage for our eventual isolation. So is this fine-tuning a clue, a coincidence, or something else entirely? The cosmological constant doesn't give up its secrets easily, but one thing's certain: the more we study it, the more we realize how little we truly understand about the rules that govern reality. And that's what makes the search so thrilling, because somewhere in this puzzle lies an answer not just about the universe, but about our place within it. The strong nuclear force operates like an invisible hand, holding the very fabric of matter together with unshakable precision. Imagine it as the cosmic glue binding protons and neutrons inside an atom's nucleus. Without it, every element heavier than hydrogen would instantly fly apart. But here's the catch: its strength isn't arbitrary. If this force were just 1% stronger, the early universe would have fused all its hydrogen into heavier elements almost immediately. Stars like our Sun, which rely on slowly burning hydrogen over billions of years, wouldn't exist. Life as we know it would have never gotten a chance to begin. On the flip side, if the strong force were even slightly weaker, protons and neutrons wouldn't stick together at all. Hydrogen might remain, but the heavier elements essential for planets, oceans, and living cells, carbon, oxygen, iron, would never form. The universe would be a dull, lifeless sea of single proton atoms with no chemistry complex enough to spark life. Yet somehow, against incomprehensible odds, the strong force is perfectly calibrated right in the middle. Strong enough to build the periodic table, but weak enough to leave fuel for stars. This razor-thin margin for error isn't just a curious detail. It's part of a pattern that stretches across physics, where even the tiniest deviation from the constants we observe would render the universe sterile. Some researchers argue this points to a deeper principle, a hidden rulebook that dictates why these forces must be exactly as they are. Others suggest we're seeing the aftermath of a cosmic lottery, where countless universes with random settings exist, and we simply inhabit the one where the numbers lined up favorably. But the strong force adds another layer to the mystery. Unlike gravity or electromagnetism, its influence drops off almost instantly over distance. It's powerful enough to overcome the fierce repulsion between positively charged protons inside a nucleus, yet it vanishes beyond that microscopic scale. This unique behavior isn't just a happy accident. It's what allows atoms to exist as stable building blocks rather than clumping into an undifferentiated mass or scattering into chaos. The more we study this force, the more it feels like the universe is playing a high-stakes game of Jenga. Every block, every constant is placed with impossible care. Remove one and the entire tower collapses. So is this perfection the result of blind chance? Or is there something or someone setting the rules? The answer could redefine not just our understanding of physics, but our place in the cosmos. And that's a question worth pulling at thread by thread until the tapestry begins to unravel. The weak nuclear force might not have the brute strength of its sibling, the strong nuclear force, but don't let the name fool you. It's a silent architect of the universe, shaping the very elements that make life possible. Picture a star like our Sun fusing hydrogen into helium in its core. That's only the first act. Without the weak force, the story would end there. It's this force that allows protons to transform into neutrons, unlocking the next chapter of stellar alchemy. When massive stars reach the end of their lives, it's the weak force that enables the creation of heavier elements like carbon, oxygen, and nitrogen, the raw materials of planets, oceans, and even our own bodies. But here's the catch: the weak force operates on a knife's edge. If it were even slightly stronger, stars would burn through their fuel too quickly, scattering heavy elements into space before they could coalesce into planets. Too weak, and those elements might never form at all. The fact that it's perfectly balanced to allow both the creation and dispersal of these building blocks is nothing short of miraculous. It's as if the universe had a recipe for life, and the weak force was the precise pinch of salt needed to make it all come together. This precision extends beyond stars. The weak force is also the reason radioactive decay happens at just the right pace to warm Earth's core, keeping our planet geologically active and its magnetic field strong, a shield against cosmic radiation that would otherwise strip away our atmosphere. Without it, Earth might be as lifeless as Mars. Yet, like the other constants we've explored, the weak force's exact strength seems almost too perfect to be accidental. So what's behind this fine-tuning? One possibility is the multiverse, a sea of universes where the weak force takes on every imaginable value. In most of them, the numbers don't add up and life never emerges. But in ours, they align just right, and here we are to ponder the odds. Others wonder if there's a deeper law of physics at work, one that naturally selects for these precise values. Either way, the weak force isn't just a footnote in the story of the cosmos. It's a pivotal character, quietly ensuring the universe doesn't just exist but thrives with us in it. And that's a mystery worth unraveling. The electromagnetic force is the invisible puppeteer behind nearly everything we experience: light, color, touch, even the very structure of matter. Imagine a world where atoms refuse to bond, where water can't form droplets, where the DNA in your cells unravels like a broken zipper. That's the reality we'd face if electromagnetism were even slightly stronger or weaker. Its strength is locked into place by a number so precise it defies logic, the fine structure constant. At roughly 1/137, this constant dictates how tightly electrons cling to their atoms, how energy dances between particles, and ultimately, whether the universe can cook up something as delicate as life. Consider this: if the fine structure constant were just 4% larger, the protons inside stars would repel each other so fiercely that nuclear fusion would sputter out. Stars, including our Sun, would never ignite. But if it were 4% smaller, atoms would lose their grip on electrons entirely, turning every molecule into a chaotic soup of free-floating particles. No water, no DNA, no chemistry complex enough to spark a single living cell. Yet here we are, in a universe where this constant sits perfectly in the narrowest of Goldilocks zones, not too strong, not too weak, but just right. This precision isn't limited to starlight and DNA. Electromagnetism shapes the very fabric of reality at every scale. It's the reason iron feels solid under your fingers, why fireflies glow in the dark, and why your nerves can send signals at lightning speed. Even the color of the sky, the way sunlight scatters into blue, is a direct result of this force's exact tuning. Change it by a hair and the world as we know it vanishes. So how did such perfection come to be? Some scientists argue it's a fluke, a statistical miracle in an ocean of possible universes where the numbers didn't align. Others see it as a clue pointing toward deeper laws we haven't uncovered yet. Laws that might naturally dictate why electromagnetism has to be this precise. Then there's the philosophical angle. Could this fine-tuning hint at something intentional, as if the universe was built with life in mind? The debate rages on, but one thing's certain: electromagnetism isn't just another entry in physics textbooks. It's the silent architect of a universe that somehow, against all odds, got the numbers exactly right. And that leaves us with a humbling thought. If the forces shaping reality had been even slightly different, we wouldn't be here to wonder about them at all. The mass of an electron seems like a tiny detail in the grand scheme of things, until you realize it's one of the universe's most carefully guarded secrets. This speck of a particle, nearly 2,000 times lighter than a proton, holds atoms together with a grip that's neither too tight nor too loose. If electrons were even slightly heavier, their extra weight would drag them spiraling into the nucleus, collapsing every atom in existence. But if they were lighter, they'd zip away like untethered balloons, leaving matter unable to form stable molecules. The result: no water, no DNA, no chemistry, just a formless void. It's as if the electron's mass was measured out with cosmic precision, like a chef adding exactly the right pinch of salt to a recipe. Now zoom in even further down to quarks, the building blocks of protons and neutrons. Their masses are even more baffling in their precision. The up and down quarks that make up atomic nuclei are fine-tuned to an almost ridiculous degree. If their masses were off by just a few percent, protons might not outnumber neutrons, or atomic nuclei might become unstable. Elements heavier than hydrogen would flicker in and out of existence, leaving the universe with nothing but a sea of lone protons. No carbon for life, no iron for planets, no gold for jewelry, just a barren wasteland of simplicity. What's striking isn't just that these masses are perfectly set, but that they're interdependent. The electron's mass balances the quark masses, which in turn balance the forces that hold atoms together. It's a house of cards where every piece relies on the others. Remove one, and the whole structure collapses. This isn't just a lucky break, it's a conspiracy of constants, as if the universe conspired to make complexity possible. So why these exact numbers? One possibility is that they're inevitable, dictated by some deeper law we haven't uncovered yet. Maybe particle masses aren't arbitrary, but are forced into these values by hidden symmetries or dimensions we can't yet perceive. String theory, for instance, suggests that the properties of particles might be tied to the geometry of tiny, curled-up dimensions, like the way a guitar string's pitch depends on its length and tension. If that's true, the masses we observe could be the only ones possible in a universe like ours. Then there's the multiverse explanation, an infinite array of universes where particles have every conceivable mass, and we just happen to live in the one where the numbers line up. But this raises its own questions. If there are countless universes with random settings, why does ours feel so meticulously arranged? Does probability alone explain the eerie harmony we see? And then there's the most provocative idea of all, that these values aren't random at all. Could there be a reason, a purpose behind the numbers? It's not necessarily about invoking a creator, but about questioning whether the universe has a built-in bias toward complexity, even life. After all, if the masses were different, we wouldn't be here to wonder about them. Whatever the answer, the precision of these particles forces us to confront a humbling truth. The universe isn't just any way. It's a specific way, a way that allows for stars, planets, and curious minds to ponder it. And that's a mystery as profound as any we've ever faced. The proton-to-electron mass ratio is one of those numbers that seems unremarkable at first glance, until you realize it's the linchpin holding chemistry itself together. Picture a proton as a bowling ball and an electron as a feather. The proton is roughly 1,836 times heavier than its tiny counterpart. That exact ratio isn't arbitrary. It's a magic number that makes the dance of atoms possible. If it were even slightly off, the delicate balance of molecular bonds would crumble, and the universe as we know it would vanish in an instant. Take water, for example. Its unique properties, the way it expands when frozen, its surface tension, even its ability to dissolve salts, all depend on the precise interplay between positively charged protons and negatively charged electrons. If protons were heavier relative to electrons, hydrogen bonds would be too weak to hold water molecules together. Lakes and rivers wouldn't exist. Life's essential solvent would evaporate into a wisp of disconnected atoms. On the other hand, if protons were lighter, electrons would orbit too loosely, making chemical reactions sluggish or even impossible. The sweet spot we live in isn't just convenient, it's non-negotiable. But it's not just water. Every molecule in your body, from the DNA in your cells to the oxygen in your blood, relies on this ratio being exactly what it is. Carbon, the backbone of life, forms stable, complex structures because protons and electrons have this specific mass relationship. Change it by even a fraction, and carbon atoms might not link up into the long chains needed for proteins or genetic material. The universe would be stuck in chemical kindergarten, forever doodling with simple atoms instead of building the elaborate structures that make life possible. What's even more startling is how this ratio connects to the other constants we've explored. The strength of the electromagnetic force, the mass of quarks, even the nuclear forces, they're all intertwined like gears in a cosmic clock. Adjust one and the others fall out of sync. This isn't a series of lucky coincidences. It's a symphony where every instrument is perfectly tuned. So why does this ratio exist at all? Some physicists argue it's a hint of something deeper, a fundamental symmetry or law we haven't uncovered yet. Others see it as evidence of a multiverse, where countless universes have random ratios, and we just happen to live in the one where chemistry works. But there's a third, more provocative possibility, that this precision isn't accidental. Could the universe have a built-in preference for complexity, even life? The proton-to-electron mass ratio doesn't just let molecules exist, it lets them dance. And in that dance, we find stars, planets, and conscious minds able to ponder the mystery of it all. That's not just a number, it's a signature one that might hold the key to understanding why the universe feels so meticulously arranged. The expansion rate of the universe isn't just a number, it's the heartbeat of cosmic history, setting the rhythm for everything that exists. Imagine the early moments after the Big Bang, when space itself began stretching at a rate so precise, it allowed galaxies to form without tearing matter apart or letting it collapse back in on itself. If the universe had expanded even a fraction faster, particles would have flown away from each other too quickly to ever coalesce into stars. No galaxies, no planets, just a cold, empty void. But if it had expanded too slowly, gravity would have pulled everything back into a fiery crunch before the first atoms could even link up. The margin for error is razor thin, like throwing a dart across a continent and hitting a bullseye the size of a single atom. What makes this even more astonishing is how the expansion rate had to sync perfectly with other cosmic parameters. Take dark energy, the mysterious force accelerating the universe's expansion today. If it had kicked in too early, galaxies would have been ripped apart before life could evolve. Too late, and the universe might have collapsed under its own weight. Instead, dark energy waited billions of years, just long enough for stars to forge heavy elements, planets to cool, and life to emerge before taking the reins. It's as if the universe had a built-in timer, ensuring everything happened in the right order. So how do we explain this precision? One possibility is the multiverse, a vast landscape of universes, each with its own random expansion rate. Most would be lifeless, but in a rare few, the numbers align perfectly, and conscious observers arise to marvel at their luck. Another idea is that there's a deeper law of physics we haven't discovered yet, one that naturally locks the expansion rate into this life-friendly value. Some theorists even speculate that the universe's expansion isn't arbitrary but follows a hidden logic, like the branches of a fractal or the harmonics of a vibration we can't yet perceive. Then there's the philosophical angle. Could the expansion rate be a clue that the universe isn't just a random accident, but something more intentional? It's not about invoking a designer, but about asking whether the laws of physics themselves might have a bias toward complexity. After all, if the universe hadn't expanded at this exact rate, we wouldn't be here to question it. That's the eerie truth at the heart of fine-tuning. The very act of observation implies a universe capable of producing observers. Whether you see this as a statistical fluke or a cosmic inevitability, one thing's clear: the expansion rate isn't just a dry fact in an astronomy textbook. It's a silent architect shaping the destiny of everything from the largest galaxy to the smallest cell. And that raises a humbling thought: the universe didn't have to be this way. But somehow, against all odds, it is. The anthropic principle sounds almost too simple at first, like the universe's way of shrugging and saying, "Well, you're here, aren't you?" But dig deeper, and this idea cracks open a door to even bigger mysteries. Think of it like a cosmic version of survivor bias. Out of all possible universes, we can only exist in one where the constants allow life. The rest, they're silent, empty, unobserved. So in a sense, the very fact we're asking these questions answers them. The universe isn't fine-tuned for life. Life is just a fluke that happened in the one universe where the numbers lined up. But here's where things get thorny. Critics say the anthropic principle feels like a dodger, a fancy way of saying it is what it is. If we accept it at face value, does that mean we stop looking for deeper explanations? After all, science thrives on asking why, not just because. Yet supporters counter that the principle isn't an endpoint, it's a starting line. It reframes the question from why these constants to why this universe, and that shift leads to mind-bending possibilities. Take the multiverse theory. If countless universes exist, each with randomly dialed constants, most would be barren. But a rare few, maybe just one, would hit the jackpot. We're in that one. It's not luck, it's inevitability. The catch, if other universes are unobservable, is this even science or just metaphysics in a lab coat? Some physicists argue that certain versions of the multiverse could leave subtle fingerprints, patterns in the cosmic microwave background, or mathematical symmetries that hint at deeper layers of reality. But for now, it's a tantalizing what if. Then there's the stronger version of the anthropic principle, which suggests the universe must produce life, not by chance, but by some inherent design. This isn't necessarily about a creator, but about the laws of physics themselves having a built-in bias toward complexity. Maybe life isn't an accident. Maybe it's a cosmic inevitability written into the fabric of reality. It's a provocative thought, one that blurs the line between physics and philosophy. So is the anthropic principle a cop-out or a revelation? Maybe it's both. It doesn't solve the mystery so much as redefine it, pushing us to ask even bigger questions. Whether you see it as a scientific shortcut or a profound insight, one thing's clear: the universe doesn't give up its secrets easily. And that's what makes the hunt so thrilling, because every answer we find seems to lead to a deeper, stranger question. Multiverse theory offers a dizzying escape from the fine-tuning problem. What if our universe isn't special, just lucky? Picture a cosmic casino with infinite slot machines, each representing a universe with randomly dialed constants. Most spit out gibberish, black holes swallowing themselves at birth, forces too weak to glue atoms together, or expansion so rapid matter never forms. But in one machine ours, the symbols line up perfectly. Life hits the jackpot. At first glance, it's an elegant solution, no need for a designer or deeper lore. The numbers had to work somewhere, but here's the catch. If the multiverse is real, why does our universe feel so meticulously arranged? Imagine walking into a library where every book is a random jumble of letters except one, which happens to be a flawless Shakespearean sonnet. You'd assume someone wrote it, not that it emerged by chance. Critics argue the multiverse doesn't solve fine-tuning, it just kicks the can down the road. Where did these infinite universes come from? Why do they follow rules allowing any stable constants at all? Even randomness has to play by some deeper physics. Then there's the testability problem. Science thrives on evidence, but how do you observe a universe beyond our own? Some theorists hunt for clues like cosmic bruises from collisions with other universes in the early cosmos, or patterns in the afterglow of the Big Bang. Others suggest the multiverse might leave mathematical fingerprints, like unexpected symmetries in particle physics. So far, no smoking gun. Detractors call it metaphysics dressed up as science, while supporters counter that unseen realms, like atoms or dark matter, were once dismissed as fantasy too. Yet the multiverse isn't just one idea, it's a spectrum. Bubble universes born from eternal inflation might each have unique physics. String theory's landscape could allow 10 to the power of 500 possible configurations. Even quantum mechanics hints at parallel worlds branching with every decision. But which version, if any, is real? The debate fractures further when you ask whether these universes exist in the same way ours does, or if they're just mathematical possibilities. What's fascinating is how the multiverse flips the fine-tuning question on its head. Instead of asking why this universe, we're forced to ask why this multiverse. If the rules generating these countless worlds are themselves finely tuned to produce even one life-friendly universe, haven't we just moved the mystery up a level? It's like discovering a factory that spits out random watches, most broken, one perfectly ticking. You'd still wonder who built the factory. Proponents see this as the ultimate naturalistic answer, no designer required, just statistics on an infinite scale. Critics call it a philosophical sleight of hand, but perhaps the truth lies somewhere in between. The multiverse might not be the final answer, but a stepping stone to something deeper. After all, every radical idea in science, from heliocentrism to quantum entanglement, started as speculation. Whether this one holds up or not, it's forcing us to think bigger than we ever have before. And that's how breakthroughs happen. String theory dances on the edge of science and philosophy, proposing a universe far stranger than we ever imagined, one where the constants of nature aren't arbitrary, but woven into the very fabric of hidden dimensions. Picture reality not as the three-dimensional stage we see, but as a symphony of tiny, vibrating strings, each note determined by the shape and size of dimensions curled up so small, they're invisible to even our most powerful microscopes. These aren't just extra spatial directions, they're the architects of reality, their geometry dictating everything from the strength of gravity to the mass of an electron. What's breathtaking about this idea is how it reframes fine-tuning. Instead of asking why the constants are so perfectly balanced, string theory suggests they couldn't be any other way. The universe isn't tuning itself, it's following rules written in the geometry of these higher dimensions. Imagine a lock with countless possible combinations, but only one set of shapes fits the key. That's what string theory proposes. Our constants are the only ones that fit the hidden structure of reality. But here's the catch: we can't see these dimensions, let alone measure them. Without experimental proof, string theory remains a beautiful hypothesis, a mathematical cathedral built on equations rather than data. Some critics argue it's not even falsifiable, the gold standard of science. Yet supporters counter that every revolutionary idea starts as speculation. General relativity was once untestable too, until starlight bending around the sun proved Einstein right. Could the same be true here? The stakes couldn't be higher. If string theory is correct, it wouldn't just explain fine-tuning. It would unify all fundamental forces into a single framework, the so-called theory of everything. Gravity, electromagnetism, the nuclear forces, all would emerge as different vibrations of the same cosmic strings. It's the kind of elegance physicists dream of, a Rosetta Stone for the universe. But until we find a way to peer into these hidden dimensions, the theory remains suspended between inspiration and frustration. So where does that leave us? For now, string theory is less a roadmap and more a compass, pointing toward possibilities we're only beginning to grasp. It doesn't answer every question, but it reframes them in ways that could, one day, lead to breakthroughs we can't yet imagine. And that's the thrill of science. The deeper we dig, the more the universe reveals how much we still have left to discover. Quantum fluctuations sound like the universe rolling dice, tiny, random jitters in the fabric of reality that might have set the cosmic constants in place. Imagine the newborn universe as a bubbling cauldron of energy where particles flicker in and out of existence in a chaotic dance. In this turbulent sea, the values we now call fundamental, the strength of gravity, the mass of electrons, could have been frozen into place purely by chance. It's a humbling thought. Our existence might hinge on a quantum whim, a fleeting imbalance in the chaos that somehow stuck. But here's the problem with pinning everything on randomness. The odds of landing on this particular set of constants, where galaxies form and chemistry works, are so vanishingly small they make winning the lottery look like a sure bet. To put it in perspective, it's like shuffling a deck of cards and getting them to arrange themselves into a perfect Shakespearean sonnet, not just once, but over and over across dozens of independent constants. Statistically, it shouldn't happen, and yet here we are. Some argue this isn't a flaw but a feature, that in an infinite multiverse, even the most improbable outcomes become inevitable. If countless universes bubble up with random constants, one will eventually hit the jackpot. But this raises a deeper question. Why does our universe feel so meticulously arranged? Randomness can explain a lot, but it doesn't account for the eerie harmony we see, the way constants interlock like gears in a watch. Change one, and the whole mechanism grinds to a halt. Then there's the curious case of quantum fluctuations themselves. Even they aren't entirely lawless. They follow the rules of quantum mechanics, operating within strict probabilities. So if randomness shaped the constants, it was randomness with a very particular set of constraints, almost as if the dice were loaded. Could there be hidden principles at work, governing even the chaos? Some theorists suggest that what we call randomness might actually be the shadow of deeper, undiscovered physics, like ripples on the surface of a pond hinting at currents below. And let's not forget the observer effect. Quantum mechanics tells us that the act of measurement can influence the outcome of an event. If consciousness emerges from the very constants set by these fluctuations, does that create a loop, a universe fine-tuned to produce observers who then, in some way, affirm its structure? It's a dizzying thought, one that blurs the line between cause and effect. So is randomness the whole story? Probably not. It might be part of the puzzle, but the precision we see suggests there's more at play, whether undiscovered laws, hidden dimensions, or something even stranger. The universe doesn't feel like a roll of the dice. It feels like a riddle waiting to be solved, and that's what makes the search so thrilling. The idea that the universe might be intentionally designed isn't new, but it takes on fresh urgency when faced with the razor's edge precision of cosmic constants. Proponents of intelligent design argue that these finely tuned parameters aren't accidents, they're signatures. Imagine finding a pocket watch in the desert. You wouldn't assume the gears aligned themselves by chance. You'd infer a watchmaker. For some, the universe's constants evoke the same conclusion, a cosmos calibrated with purpose. But here's where things get thorny. Science thrives on testable hypotheses, and design, by its nature, resists easy experimentation. How do you prove intent in the laws of physics? You can't rerun the Big Bang to see if life-friendly settings emerge twice. Yet design advocates point to the sheer improbability of our universe's balance as circumstantial evidence. The odds of landing on these constants randomly are so absurdly low that invoking chance feels, to them, like explaining a Shakespearean sonnet as the result of a monkey randomly hitting keys. Critics counter with two objections. First, improbability alone doesn't imply design. It might just mean we don't yet understand the rules. Before plate tectonics, earthquakes seemed like acts of gods. Second, invoking a designer raises an infinite regress. Who designed the designer? If the universe requires a fine-tuner, wouldn't that entity need one too? Some philosophers sidestep this by suggesting the designer exists outside time, or that the laws of physics themselves are the mind of the cosmos, self-contained and self-explanatory. Then there's the middle ground. Some scientists, uncomfortable with both pure chance and supernatural explanations, explore a third option. What if the universe's laws naturally evolve toward complexity? Think of it like a cosmic version of natural selection, where only self-consistent, stable universes survive long enough to be observed. It's not design in the traditional sense, but it's not blind luck either. It's a dynamic process favoring certain outcomes. The debate exposes a fascinating tension in how we seek answers. Science aims for mechanisms, while philosophy and theology grapple with meaning, but perhaps they're not mutually exclusive. Even if design lies beyond empirical proof, the question itself pushes us to dig deeper, to ask whether the universe's order hints at something more than equations on a chalkboard. After all, the same fine-tuning that fuels this debate also made it possible for us to have it, and that's a mystery worth sitting with, no matter where you stand. The fine-tuning of the universe isn't just a scientific puzzle, it's a mirror held up to our deepest beliefs about existence itself. For centuries, philosophers and theologians have wrestled with the same question scientists now confront. Does the precision of cosmic constants hint at something beyond mere chance? Some see the hand of a creator in the delicate balance of forces that make life possible. Others argue nature follows laws we don't yet fully understand, rendering the idea of design unnecessary. This divide isn't just academic, it strikes at the heart of how we see our place in the cosmos. Take the classical design argument, which traces back to thinkers like Thomas Aquinas and William Paley. They observed order in nature, the way planets orbit the sun, or the intricate structures of living cells, and concluded such harmony couldn't arise without intention. Modern fine-tuning updates this ancient idea with razor-sharp physics. When cosmologists calculate that altering a single constant by a hair would render the universe lifeless, it's hard not to wonder, is this the mark of a craftsman? Even atheist philosopher Antony Flew, after decades of skepticism, conceded that fine-tuning seemed to point toward an Aristotelian god who set the universe in motion with exquisite care. Yet not everyone finds this persuasive. Critics counter that invoking a designer merely replaces one mystery with another. Who designed the designer? If complexity requires explanation, wouldn't a divine mind be even more complex? Some scientists, like Stephen Hawking, argued that the multiverse could dissolve the need for design entirely. With infinite universes, a life-permitting one becomes statistically inevitable. But this shifts the debate rather than resolves it. Why does any universe exist at all? Why these particular laws governing the multiverse? The questions spiral outward, leaving us with a choice: accept an endless chain of causes or posit something beyond the physical. Then there's the middle path, philosophical naturalism, which seeks to explain fine-tuning without supernatural leaps. Perhaps the constants aren't arbitrary but emerge from deeper, undiscovered principles. Just as Einstein's equations revealed gravity as the curvature of space-time, maybe future physics will show why the fine structure constant must be 1/137. String theory's hidden dimensions or quantum gravity symmetries could one day reveal a universe that tunes itself. Until then, the mystery remains open, a frontier where science and philosophy collide. What makes this debate so gripping is how it transcends disciplines. A physicist calculating the odds of our universe's constants shares the same awe as a monk contemplating the divine. Both confront the same staggering improbability, that against inconceivable odds, here we are, conscious and questioning. Whether you see that as destiny or accident, the fine-tuning problem invites us to look beyond equations and ask the oldest question of all: why is there something rather than nothing? And in that question, science and spirit meet. Not everyone sees the universe's fine-tuning as proof of something deeper. For some scientists, it's less a cosmic mystery and more a gap in our understanding, a puzzle waiting for the right piece to snap into place. Imagine standing in front of a locked door, convinced there's no key, only to realize later you were holding it all along. That's the heart of scientific skepticism. The constants might seem arbitrary now, but future breakthroughs could reveal they're as inevitable as the rising sun. Take the history of physics as a guide. A century ago, the behavior of atoms seemed inexplicable until quantum mechanics rewrote the rules. Before that, Newton's laws felt absolute until Einstein showed they were just one piece of a larger puzzle. Every era has its unsolved questions, and every generation assumes they've hit the limits of knowledge until they haven't. Could the fine-tuning problem be the same? A temporary blind spot, not a fundamental feature of reality. Critics of fine-tuning argue that calling these constants perfect is a tautology. Of course, they appear perfectly set for life. We're here to observe them. If they were different, we wouldn't exist to notice. It's like a puddle marveling at how perfectly its hole fits its shape. The universe isn't tailored for us. We've simply adapted to its rules. This perspective flips the script. Instead of asking why the constants are life-friendly, we should ask why life evolved to match the constants. Then there's the possibility of undiscovered physics. What if the constants aren't independent dials but interconnected gears, all turning in sync because of some deeper principle? String theory hints at this, suggesting that hidden dimensions could lock constants into place. Or perhaps there's a yet-to-be-discovered symmetry in nature, a mathematical rule that forces these values into their precise positions. If that's true, the fine-tuning problem vanishes. The numbers couldn't be any other way. But skepticism doesn't mean dismissal. Even those who doubt fine-tuning as evidence of design admit the numbers are staggeringly precise. The debate isn't about whether the constants are finely tuned, it's about what that tuning implies. Is it a clue, a coincidence, or just a placeholder for knowledge we haven't uncovered yet? Science thrives on these tensions, the push and pull between mystery and explanation. What's fascinating is how this skepticism fuels progress. The harder we stare at the fine-tuning problem, the more creative our theories become. Maybe the answer lies in a grand unification of forces or a radical rethink of causality itself. Or maybe, just maybe, we're asking the wrong questions altogether. After all, the universe owes us no explanations. It simply is, and that's what makes the search so thrilling. Whether you see fine-tuning as a signpost or a mirage, one thing's certain: the conversation is far from over. What if the constants of physics aren't set in stone but shift like sand over cosmic time? This radical idea turns the fine-tuning problem on its head. Instead of asking why the numbers are perfect now, we'd ask how they became perfect. Picture a universe where gravity weakens by a fraction every billion years, or the speed of light slows imperceptibly over epochs. In such a world, today's delicate balance might not be a starting point but an endpoint, the result of a slow, cosmic evolution that naturally sifts out life-friendly conditions. This isn't just speculation. Theories like variable speed of light cosmology or dynamic dark energy models suggest that what we call constants might be more like habits, patterns the universe settles into after countless cycles of trial and error. Think of it like a river carving a canyon. The water doesn't plan the path, but over time it finds the most stable route. Similarly, if the laws of physics can adjust, even randomly, universes that stumble into stable configurations like ours would persist long enough for life to emerge. The rest, they'd collapse or dissipate before anyone could notice. One compelling version of this idea comes from physicist Lee Smolens's cosmological natural selection. Imagine black holes as cosmic nurseries, each birthing a new universe with slightly tweaked constants. universes that produce more black holes, meaning they're stable enough for stars to form and die, get more offspring. Over countless generations, the universes that dominate the multiverse would be those like ours, finely tuned for star formation and, by extension, life. No designer needed just a slow, evolutionary winnowing of possibilities. But how would we test such wild ideas? Some researchers hunt for subtle traces of changing constants in the light from distant quasars or the decay of ancient meteorites. If the fine structure constant or proton mass varied even slightly over billions of years, it might leave fingerprints in these cosmic archives. So far, the evidence is inconclusive, but the search is young. Other clues might come from the cosmic microwave background, where imprints of the universe's infancy could reveal if today's constants were different at the dawn of time. What's fascinating about these models is how they reframe fine-tuning from a stroke of luck to an inevitable outcome. If physics evolves, then life-friendly universes aren't improbable, they're inevitable given enough time and cycles. It's a middle path between chance and design, where the universe isn't made for life but grows into it. Of course, skeptics point out the gaps. If constants change, what governs the rules of their change? Doesn't that just push the mystery up a level? And without direct evidence, these theories remain elegant speculation. But that's the beauty of science at the frontier. The best ideas often sound like fiction until they don't. Whether these models hold up or not, they remind us that the universe might be far more dynamic, far more alive than we ever imagined. And that's a thrilling possibility to explore. What if our universe isn't the ultimate reality, but something more like an advanced video game, a simulation crafted by beings so far beyond us, their motives are as mysterious as the code running our existence? This is the simulation hypothesis, an idea that's equal parts science fiction and serious philosophy. Think of it like this: if future civilizations could create hyper-realistic virtual worlds inhabited by conscious beings, why wouldn't they? And if that's possible, how could we ever prove we're not one of those simulations ourselves? Suddenly, the fine-tuning of the universe takes on a whole new meaning. Those perfectly balanced constants might not be laws of nature at all, just parameters programmed into the system. The eerie thing is, this isn't entirely untestable. Some scientists, like physicist Silas Bean, have proposed looking for glitches in the fabric of reality, tiny imperfections that might reveal the underlying code. Imagine finding pixel-like patterns in the cosmic microwave background, or mathematical anomalies in high-energy particle collisions. Others suggest that if our universe is a simulation, it might run on finite computational resources, meaning extremely small-scale phenomena could appear fuzzy or simplified under close scrutiny. It's like searching for the seams in a digital universe, hunting for places where the rendered distance drops off or the physics engine cuts corners. But the simulation hypothesis isn't just a modern twist on creation myth, it's also a mirror for our own technological trajectory. We're already building increasingly sophisticated virtual worlds, from AI-driven NPCs in video games to rudimentary simulations of quantum systems. If this trend continues, it's not absurd to imagine a future where entire civilizations could be simulated down to the last atom. And if that's possible, the statistical odds tilt heavily toward us already living in one. After all, there might be countless simulated universes for every base reality. Yet for all its intrigue, the hypothesis raises unsettling questions. If we're in a simulation, who or what is running it? Are we someone's experiment, a form of entertainment, or even an ancestor simulation designed to recreate lost history? And what happens if the simulators decide to shut it down? These aren't just thought experiments, They echo age-old philosophical dilemmas about the nature of existence, free will, and whether reality is as solid as it seems. Skeptics, of course, point out the lack of concrete evidence. Until we find those cosmic glitches, the simulation hypothesis remains a tantalizing what if. But whether you find it plausible or far-fetched, it forces us to confront the strangeness of our universe's fine-tuning from a fresh angle. Maybe the constants aren't accidents or divine gifts, but deliberate settings in a reality we're only beginning to question. And that's a possibility as exhilarating as it is humbling. Cosmic inflation paints a dramatic picture of the universe's first moments, a runaway expansion so violent it stretched space itself smoother than glass in a fraction of a second. This wasn't just rapid growth, it was a cosmic reset button, ironing out wrinkles in spacetime that might otherwise have collapsed the universe into black holes or torn it apart into chaos. But here's the twist. Some versions of inflation don't just explain why the universe looks uniform. They suggest it's constantly birthing new universes, each with its own unique set of physical constants. Imagine a bubbling foam of realities, where every bubble inflates into a full-fledged cosmos, its laws of physics frozen into place by random quantum fluctuations during that explosive infancy. At first glance, this seems like the ultimate answer to fine-tuning. If inflation generates infinite universes with every possible combination of constants, then of course one of them, ours, would end up with the perfect recipe for life. No designer needed, no cosmic lottery too improbable. It's the multiverse on steroids, with inflation as the engine churning out endless variations. But dig deeper, and the mystery doesn't dissolve, it relocates. Why does inflation itself operate by rules that allow this creative chaos? The theory requires its own precise fine-tuning. The energy density of the inflationary field, the rate of expansion, even the way it transitions to the slower growth we see today. Tweak any of these, and the whole mechanism falls apart. Take the flatness problem, one of inflation's great successes. Our universe is astonishingly flat on large scales, meaning space isn't curved enough to collapse or tear apart. Inflation explains this by stretching spacetime until any initial curvature becomes negligible. But for that to work, the inflationary field had to decay at just the right moment, too soon, and the universe would remain lumpy, too late, and it would have expanded so fast that no galaxies could ever form. It's as if the universe had a built-in timer set to a trillionth of a second, a precision that echoes the very fine-tuning inflation was meant to explain away. Then there's the multiverse loophole. Even if inflation spawns countless universes, why should any of them have stable constants? The process relies on quantum fluctuations, which are inherently random. You'd expect most bubbles to be stillborn, collapsing instantly or fizzling into formless energy. The fact that even one universe like ours exists with constants balanced so delicately suggests something deeper might be at play. Perhaps inflation isn't purely random but follows hidden rules that favor complexity. Some theorists, like Andre Lind, propose that certain inflationary fields naturally settle into life-friendly configurations over time, like a ball rolling to the bottom of a valley. But this just shifts the fine-tuning up a level. Why should the landscape of possible fields have valleys at all? The real puzzle isn't whether inflation happened. The evidence is compelling, but what it implies about the nature of reality. If our universe is one bubble in an endless froth, are the others testable? Some scientists hunt for bruises in the cosmic microwave background, anomalies where our bubble might have collided with another. Others look for statistical fingerprints in the distribution of galaxies. So far, no smoking gun, and that's the irony. The more elegant inflation becomes as a theory, the more it feels like a cosmic sleight of hand. It doesn't erase the fine-tuning problem. It rephrases it in a grander, more enigmatic language. So where does that leave us? Inflation might be the best explanation we have for the universe's smoothness and structure, but it turns out to be a double-edged sword, solving some mysteries while deepening others. Whether you see it as a key to the multiverse or just another layer of the puzzle, one thing's clear: the universe's constants didn't fine-tune themselves by accident. The real question is whether they were set by necessity, chance, or something even stranger, and that's a mystery inflation alone can't solve. Dark energy is the universe's most enigmatic architect, a force so subtle it's practically invisible, yet powerful enough to dictate the fate of everything. Picture it as an anti-gravity pushing galaxies apart faster and faster, stretching the cosmos into an ever-cooling emptiness. But here's what baffles scientists: its strength isn't just small, it's improbably small. Calculations suggest the natural value of dark energy should be a staggering 120 orders of magnitude larger than what we observe. That's like expecting a tidal wave and getting a single, hesitant ripple instead. And that ripple is the only reason we're here to notice it. If dark energy were even slightly stronger, the universe would have blown itself apart before stars could ignite. Imagine a cosmic tug of war where one side suddenly lets go. Matter would have flown outward so violently that galaxies, planets, and even atoms could never have clumped together. The universe would be a featureless void, expanding into oblivion before the first spark of complexity could emerge. On the other hand, if dark energy were weaker, or worse, negative gravity would have won out long ago, collapsing everything back into a fiery crunch. The fact that it's balanced on this knife's edge isn't just luck, it's a cosmic tightrope act with no safety net. What makes this even stranger is timing. Dark energy didn't dominate the universe's expansion until after galaxies had formed. For billions of years, gravity held sway, allowing matter to gather into the vast webs of stars and galaxies we see today. Then, around 5 billion years ago, dark energy quietly took the wheel, accelerating the expansion just enough to prevent collapse, but not so much as to tear everything apart. It's as if the universe had a built-in delay, ensuring life had time to arise before the lights began to dim. So why this precise calibration? One possibility is the multiverse, countless universes where dark energy takes on every conceivable value, and we simply inhabit the rare one where it's survivable. But even that feels unsatisfying. If dark energy can vary so wildly, why is our value not just life permitting but optimized? Some researchers argue there might be an undiscovered law capping its strength, a kind of cosmic speed limit preventing it from overwhelming gravity entirely. Others wonder if dark energy isn't a constant at all, but a field slowly decaying over time, its current value just a snapshot in a much longer story. Then there's the existential angle. Dark energy doesn't just explain the past, it forecasts the future. At its current rate, it will eventually push galaxies beyond our cosmic horizon, leaving future civilizations with a night sky devoid of stars. The universe will grow cold, dark, and lonely, a fate that feels almost poetically bleak. But here's the twist: without dark energy's exact balancing act, none of that future, or our present, would exist at all. Whether you see this as a fluke or a clue, one thing's certain: dark energy isn't just another entry in the catalog of cosmic mysteries. It's a silent conductor, orchestrating the universe's expansion with a precision that defies explanation. And that leaves us with a haunting question: is its perfection an accident or the signature of something deeper? The answer, like dark energy itself, remains just out of reach. Entropy is the silent sculptor of the universe, shaping everything from swirling galaxies to the thoughts in your brain. But here's the catch: it didn't start at zero. The early universe had just enough order, just enough structure to set the stage for everything that followed. If entropy had been even slightly higher at the Big Bang, matter would have scattered into a formless haze, never clumping into stars or planets. Too low, and the cosmos would have frozen into a rigid, unchanging crystal, devoid of motion or change. The fact that it was balanced precisely in between, a whisper of structure amid the chaos, is one of the most underappreciated examples of fine-tuning. Think of entropy like a deck of cards. A brand new deck comes perfectly ordered ace through king, suits neatly separated. Shuffle it once, and it's slightly disordered. Shuffle it 1,000 times, and it's random. Now imagine the universe started with the deck already shuffled. No order, no patterns, just chaos from the outset. Complex structures like galaxies or DNA could never emerge, but instead, the universe began with the deck nearly stacked, full of potential energy waiting to be spent. Why? That's the million-dollar question. Some physicists argue this low initial entropy points to something deeper, a hidden law or symmetry that forced the early universe into this improbable state. Others, like Nobel laureate Roger Penrose, calculate the odds of such a low entropy beginning as so absurdly small that invoking chance feels inadequate. It's like tossing a coin and getting heads a googol times in a row. The numbers defy belief. Then there's the arrow of time. Entropy is why we remember the past but not the future, why ice melts in your drink but never spontaneously refreezes. Without that initial low entropy, time itself wouldn't have a direction. Causality would blur, and the universe would lose its narrative flow. No stars burning, no life evolving, just a static soup of particles with no before or after. So where does this leave us? The universe's entropy wasn't just a starting condition. It was a golden ticket, a one-time offer that made complexity possible. Whether it's a clue to deeper physics, a signature of something beyond our cosmos, or just a staggering fluke, one thing's clear: the universe didn't have to be this way. And yet, here we are, in a reality where disorder unfolds just slowly enough to let wonders like us emerge and wonder why. Biological fine-tuning stretches the mystery of cosmic constants down to our own planet, where an intricate web of conditions makes life not just possible, but sustainable. Take Earth's position in the solar system, a seemingly ordinary orbit around a middle-aged star. But shift our planet just 5% closer to the sun, and oceans would boil away. Move it 15% farther out, and ice would lock the world in a permanent winter. This Goldilocks zone isn't just about temperature, it's about timing. The sun's gradual brightening over billions of years happened to align perfectly with Earth's ability to regulate its climate through plate tectonics and carbon cycles. Like a celestial dance where every step is choreographed to avoid catastrophe. Then there's the atmosphere, a delicate cocktail of nitrogen, oxygen, and trace gases that shouldn't exist in such balance. Oxygen makes up 21% of our air, a number that feels almost arbitrary until you realize it's the sweet spot between fire and suffocation. A few percent higher and wildfires would rage uncontrollably. A few percent lower and complex life couldn't metabolize enough energy to evolve brains capable of pondering these questions. Even the seemingly random presence of an ozone layer, a fragile shield against lethal ultraviolet rays, depends on atmospheric chemistry so precise it borders on alchemy. But the moon, often romanticized, rarely credited as a biological necessity, might be the most underrated piece of the puzzle. Its massive size relative to Earth stabilizes our axial tilt, preventing wild climate swings that would render seasons chaotic and unpredictable. Without that gravitational anchor, Earth's poles could shift dramatically over millennia, turning rainforests into tundras and deserts into ice sheets. The moon's gentle tug also drives tides, which some scientists argue played a crucial role in mixing the primordial soup where life first stirred. What's striking isn't just that these conditions exist, but how they reinforce one another. Earth's magnetic field, generated by a churning molten core, deflects solar winds that would otherwise strip away our atmosphere. That same core fuels volcanic activity, recycling carbon and other elements essential for life. Even Jupiter, lurking in the outer solar system, acts as a cosmic bodyguard, its gravity diverting asteroids that might otherwise bombard Earth into sterility. It's a system of interconnected safeguards, each one improbably precise on its own, but together they form a tapestry of fine-tuning so intricate it defies mere chance. So is this a cosmic blueprint or a series of lucky breaks? One camp argues that in a universe vast enough, even the rarest accidents become inevitable. With countless planets orbiting countless stars, at least one was bound to hit the jackpot. Others see a deeper pattern, a hint that the laws of physics and chemistry might naturally favor complexity, nudging the universe toward life where conditions allow. There's even a radical idea called the Gaia hypothesis, which suggests Earth's biosphere actively regulates itself to maintain habitability, like a self-correcting engine. Yet for all these theories, the haunting question remains: how many of these accidents can we stack before they stop feeling like accidents? Earth didn't just win the lottery once, it kept winning over and over across billions of years. Whether you call that destiny, luck, or something beyond our current understanding, one thing's certain: we're here because an astonishing sequence of events lined up with impossible precision. And that realization doesn't just deepen the mystery of our existence, it redefines it. The Fermi paradox cuts to the heart of the fine-tuning mystery with a single, haunting question: if the universe seems tailor-made for life, why does it feel so empty? Imagine walking into a banquet hall set with 1,000 plates, each perfectly arranged with gleaming silverware and fresh flowers, only to find you're the sole guest. That's the eerie contradiction at play, a cosmos exquisitely calibrated for life, yet one where we've found no definitive trace of other civilizations. Some scientists argue this silence is the ultimate clue, proof that even in a life-friendly universe, the leap from chemistry to consciousness might be astronomically rare. Consider the great filter hypothesis. Perhaps fine-tuning gets life to the starting line, but some nearly insurmountable obstacle, a galactic bottleneck, prevents most civilizations from reaching the stars. It could lurk in our past. Maybe DNA itself is a 1 in a trillion fluke. Or worse, it might await us in the future: nuclear war, runaway AI, or some unknown catastrophe that snuffs out advanced societies before they can spread. If the filter is ahead of us, that casts humanity's fate in a chilling new light. Yet others see the paradox differently. What if we're not alone, but simply early? The universe spent its first billion years too hot for complex chemistry, and stars like our sun are relative latecomers. Intelligent life might still be rare, but not because the dice didn't land right, because the game is young. In this view, we're pioneers in a cosmos just waking up to its potential, like the first bird singing at dawn. Then there's the cosmic zoo hypothesis. Maybe advanced civilizations exist but choose not to reveal themselves, observing us like wildlife in a galactic nature preserve. Or the answer could be far stranger: what if life routinely emerges, but transcends physical form before we can detect it? Some theorists speculate that sufficiently advanced intelligence might abandon biological bodies entirely, uploading into quantum substrates or higher dimensions beyond our perception. The paradox forces us to confront an unsettling possibility. That fine-tuning doesn't guarantee company. The universe might be a stage set for life, but the audience could be smaller than we ever imagined. Or perhaps we're missing the point entirely. If the cosmos is fine-tuned not just for life but for meaning, then our solitude isn't a bug, it's a feature. The universe might not need a crowd of civilizations to fulfill its purpose. One curious, questioning species could be enough. Whatever the truth, the intersection of fine-tuning and the Fermi paradox reshapes how we see our place in the grand scheme. Are we a cosmic accident, a statistical inevitability, or something even more profound? The silence of the stars might not be emptiness after all, but a mirror, reflecting back the deepest questions about who we are and why we're here. The next decade could rewrite our understanding of the cosmos, as cutting-edge telescopes and particle colliders begin hunting for answers to the fine-tuning puzzle. Imagine the James Webb Space Telescope's successors, like the proposed Habitable Worlds Observatory, scanning exoplanet atmospheres for biosignatures, not just to find life, but to test whether Earth's delicate balance is unique or a cosmic commonplace. Meanwhile, underground labs like the Deep Underground Neutrino Experiment will probe the quirks of quantum particles with unprecedented precision, searching for anomalies that might hint at hidden dimensions or new forces. These experiments aren't just incremental steps, they're potential game changers, offering the first real data to test whether our universe's constants are locked in place by deeper laws or frozen accidents of cosmic history. Then there's the hunt for gravitational waves from the earliest moments of the Big Bang. Future observatories like the Laser Interferometer Space Antenna could detect ripples in spacetime that carry echoes of inflation, the explosive expansion that may have birthed countless other universes. If those waves bear patterns suggesting collisions with neighboring bubble universes, it would be smoking gun evidence for the multiverse, transforming fine-tuning from a philosophical quandary into a measurable phenomenon. Even a null result would be profound, ruling out entire classes of theories and forcing physicists back to the drawing board. Particle colliders, too, are entering uncharted territory. The high-luminosity LHC upgrade will smash protons with such energy that it might produce particles predicted by supersymmetry, a theory that could explain why the Higgs boson's mass, and by extension the stability of atoms, is so improbably fine-tuned. If these particles appear, they'd reveal a hidden symmetry weaving through reality, one that naturally cancels out the quantum fluctuations threatening to destabilize matter. Or perhaps colliders will uncover something entirely unexpected, a fifth fundamental force, extra dimensions curled up like microscopic origami, or even evidence that constants aren't constant at all but vary subtly over time. Cosmologists are also turning to the cosmic microwave background with sharper tools than ever. The Simons Observatory and future CMB-S4 project will map this afterglow of the Big Bang in exquisite detail, searching for statistical anomalies, tiny deviations from randomness that could betray the presence of other universes nudging ours during inflation. Others are developing quantum sensors to test whether gravity behaves differently at microscopic scales, a potential clue that Einstein's theory merges with quantum mechanics in ways that mandate our universe's precise tuning. What makes this era so electrifying isn't just the technology, but the sheer breadth of possibilities. For the first time, we're not just speculating about multiverses or hidden symmetries, we're building machines to catch them in the act. And if the answers lie beyond our current grasp, that's equally thrilling. A null result would mean the universe's fine-tuning is even more mysterious than we thought, pushing us toward radical new physics or philosophical paradigms. Either way, the journey promises to be as transformative as the destination. After centuries of wondering why the cosmos seems crafted for life, we're finally assembling the tools to ask the universe directly, and it might just whisper back. Philosophers of science have wrestled with the fine-tuning problem for decades, but their debates aren't just about the answers, they're about whether we're even asking the right questions. On one side, thinkers like Karl Popper might argue that fine-tuning isn't truly scientific because it's unfalsifiable. If we can't imagine an experiment to disprove it, does it belong in the realm of physics or metaphysics? This camp sees the constants as brute facts, no more mysterious than the value of pi or the speed of light. To them, asking why they're life-friendly is like asking why the sky is blue. It just is, and science describes it without needing deeper justification. Yet others, inspired by thinkers like Thomas Kuhn, counter that science has always expanded into territories once deemed philosophical. Dark matter was once a speculative fix for galactic rotation. Now it's a pillar of cosmology. The fine-tuning problem, they argue, might follow the same path, a puzzle waiting for the right paradigm shift. Imagine a 16th century scholar dismissing the question of planetary motion as metaphysical before Kepler cracked the code of elliptical orbits. Could today's fine-tuning debate be the prelude to a similar revolution? The divide often boils down to what we consider scientific. For empiricists, only testable claims count. But for realists, the sheer improbability of our constants demands explanation, even if it pushes the boundaries of current methods. This tension isn't just academic, it shapes how we fund research, frame hypotheses, and interpret anomalies. When the Large Hadron Collider confirmed the Higgs boson, it validated decades of theory. But what if the answers to fine-tuning lie beyond colliders, in realms we can't yet observe, like the landscape of string theory or the structure of a multiverse? Does that make them unscientific or simply science in its infancy? Some philosophers, like David Deutsch, take a provocative middle ground. They argue that fine-tuning isn't a problem to solve but a clue that our current theories are incomplete. In his view, every major leap in science from Copernicus to quantum mechanics came from confronting impossible coincidences head-on. The universe's constants might be the next frontier, hinting at deeper laws that naturally select for stability and complexity. It's not about invoking designers or multiverses, but about recognizing that our current physics is a rough draft, missing entire chapters. Then there's the pragmatic perspective. Whether fine-tuning is ultimately scientific or metaphysical, its implications are undeniable. It forces us to confront the limits of knowledge, the nature of explanation, and whether the universe is ultimately intelligible. These aren't just abstract musings, they're the bedrock of how we explore reality. And perhaps that's the most profound lesson of all. The fine-tuning debate isn't just about the universe's constants. It's about us, our curiosity, our methods, and our unshakable drive to find meaning in the numbers. The idea of a finely tuned universe doesn't just live in textbooks, it's seeped into our stories, our art, and the way we imagine our place in the cosmos. Take science fiction, where alternate universes with tweaked constants have become a narrative playground. Shows like Rick and Morty or novels like Philip Pullman's His Dark Materials explore worlds where gravity behaves differently, time flows backward, or life evolves under alien physics. These aren't just whimsical thought experiments, they're reflections of our fascination with the eerie precision of our own reality. What if the speed of light were slower? What if atoms couldn't bond? These stories let us toy with the fragile balance of existence, turning cosmic fine-tuning into a canvas for imagination. But it's not just fiction. The fine-tuning debate has echoed through religious and philosophical thought for centuries. The medieval concept of the great chain of being, with its belief in a harmonious, purpose-built universe, mirrors modern awe at life-friendly constants. Today, theologians and atheists alike grapple with the same question. Does the universe's precision hint at intention, or is it a statistical fluke? This tension fuels everything from TD talks to late-night dorm room debates, because at its core, fine-tuning isn't just about physics, it's about whether reality itself has a why. Even music and visual art have drawn from this well. Album covers like Pink Floyd's Dark Side of the Moon or sculptures like Anish Kapoor's Cloud Gate evoke a sense of cosmic order, of hidden symmetries waiting to be decoded. Filmmakers like Christopher Nolan use fine-tuning as narrative stakes. Interstellar's climax hinges on a fifth-dimensional future where humanity manipulates gravity to save itself. These works tap into something primal, the human craving to find patterns, to believe the universe isn't just random noise but a story with meaning. Why does this concept grip us so deeply? Perhaps because fine-tuning sits at the crossroads of science and spirituality, offering a rare space where equations and existential questions collide. In a world increasingly fragmented by data and dogma, the idea that the cosmos might be just right for life feels like a unifying mystery. It's not about proving or disproving a creator. It's about recognizing that the universe, against all odds, permits curiosity. And that's a tale as old as time, retold in every culture's myths, equations, and art. Whether through equations or allegories, we keep asking the same thing. Are we here by accident, or is the cosmos whispering a secret we're only beginning to hear? If the universe is indeed fine-tuned for life, that revelation doesn't just reshape our understanding of physics, it tugs at the very fabric of our moral compass. Think about it. If the constants of nature align with such improbable precision to allow our existence, does that come with an unspoken responsibility? For some, the answer is a resounding yes. This perspective frames humanity as cosmic custodians, entrusted with safeguarding not just Earth, but any life that might exist beyond it. After all, if the universe went to such lengths to create the conditions for consciousness, squandering that gift through environmental neglect or reckless expansion would feel like a profound betrayal. It's the difference between seeing ourselves as accidental tourists in an indifferent cosmos versus intentional participants in a story far grander than we've yet grasped. But stewardship isn't the only ethical lens. For others, fine-tuning is less about obligation and more about opportunity, a cosmic green light to explore, innovate, and push the boundaries of knowledge. If the universe is built for discovery, then our moral imperative might be to fulfill that potential, whether by venturing to other stars, deciphering the laws of reality, or even one day seeding life elsewhere. This view resonates with the legacy of pioneers like Carl Sagan, who saw space exploration not as a luxury but as an evolutionary necessity. The stakes here aren't just philosophical, they're survival. A single asteroid, a self-inflicted climate catastrophe, or a technological misstep could erase billions of years of cosmic fine-tuning in an instant. Ethical urgency, then, isn't just about preserving what we have. It's about ensuring life's flame doesn't flicker out before it can spread beyond this pale blue dot. Yet these positions aren't mutually exclusive. The same fine-tuning that makes Earth's biosphere so fragile also equips us with the tools to protect and extend it. Renewable energy, ecosystem restoration, even plans for planetary defense against asteroids, all emerge from the unique blend of curiosity and foresight that a life-friendly universe permits. There's a poignant symmetry here. The laws that allowed stars to forge the carbon in our bones also gave us the intellect to comprehend them. That duality invites a third perspective, one that sees fine-tuning not as a mandate or a license, but as an invitation to partnership. We're not just beneficiaries of a finely tuned cosmos, we're its active collaborators tasked with weaving its potential into something enduring. But tread carefully, this line of thought has shadows. If we're alone in a life-friendly universe, the ethical weight grows heavier. Every extinction event we fail to prevent, every resource we exhaust, becomes a theft from a cosmic ledger that might never balance again. Conversely, if life is abundant, our responsibilities shift. Do we have a duty to seek out and uplift other civilizations, or would interference violate some unspoken prime directive? These aren't hypotheticals, they're questions we'll face as spacefaring species, and the answers will define not just our morality, but our legacy. Perhaps the most unsettling implication is temporal. Fine-tuning suggests the universe had to wait billions of years for life to emerge. If we're its culmination or even a stepping stone, then our choices ripple across epochs. Ethical failures today could echo through millennia, closing doors for civilizations unborn. It's a humbling thought. In a cosmos where constants conspired to make us possible, our actions might determine whether that conspiracy was worth it. So where does that leave us? However we interpret fine-tuning's ethical call, one thread binds all perspectives. The universe didn't have to be this way. Its precision, whether purposeful or providential, demands we rise to the occasion not as conquerors or caretakers, but as conscious participants in a reality far stranger and far more precious than we ever imagined. Critics of the fine-tuning argument often highlight a fundamental logical flaw, the problem of selection bias. We exist in this particular universe with these specific constants, precisely because they allow for our existence. It's like a lottery winner marveling at their luck while ignoring the millions who didn't win. If the constants were different, we wouldn't be here to ponder them. This observation, known as the anthropic principle, suggests that what appears to be astonishing precision might just be a cosmic version of survivorship bias. The universe isn't fine-tuned for us. We're the inevitable product of a universe that happened to meet the bare minimum requirements for life. Another critique challenges the very premise that constants could be different. What if the values we observe aren't independent dials but locked into place by deeper, undiscovered laws? Imagine a game where the rules only allow one possible outcome. No matter how many times you play, the result is always the same. Some physicists argue that the constants might emerge from a unified theory, like pieces of a puzzle that only fit together one way. String theory, for instance, proposes that the geometry of hidden dimensions could naturally fix constants like the fine structure constant or the mass of an electron. If true, the idea of fine-tuning collapses. These values aren't adjustable, they're inevitable. Then there's the issue of what we even mean by life-friendly. Critics argue that our definition is hopelessly narrow, biased by the only example of life we know, us. Could there be forms of life built on entirely different physics structures that thrive in a universe with stronger gravity or weaker electromagnetism? Silicon-based life, plasma-based intelligence, or even conscious patterns in the fabric of spacetime itself. If life isn't limited to carbon and water, then the range of habitable universes might be far wider than we assume. The fine-tuning argument, in this view, is like a fish declaring water is the only possible medium for existence, unaware of creatures that breathe air. Skeptics also question whether the fine-tuning problem is even a scientific question at all. Science relies on testable hypotheses, but how do you test whether constants could have been different? Without observable alternate universes or experiments to tweak fundamental physics, the debate risks slipping into metaphysics. Some argue that invoking fine-tuning is a placeholder for ignorance, a way of saying, we don't know yet, dressed up as a profound mystery. Historically, many miraculous phenomena, from eclipses to diseases, were eventually explained by natural laws. Could the same be true here? Yet the most compelling critiques don't dismiss fine-tuning outright, they reframe it. Even if the constants aren't adjustable, their precise values still demand explanation. Why this set of laws and not another? The debate isn't about dismissing the mystery, but about where to direct our curiosity. Is fine-tuning a clue pointing to deeper physics, a statistical fluke, or something beyond our current understanding? The answer, if there is one, lies not in cherry-picking evidence but in wrestling with the full complexity of the cosmos. And that's what makes this debate so vital. It's not just about the universe's rules, but about how we uncover them. The fine-tuning of the universe isn't just a scientific puzzle, it's a deeply personal one. Staring at those razor-thin margins that allow our existence, it's hard not to feel a mix of awe and unease. For some, it's a whisper of something greater, a cosmic fingerprint hinting at intention behind the numbers. A theologian might see divine craftsmanship in the way gravity and electromagnetism balance like clockwork, while a spiritual skeptic could interpret it as evidence of a universe that's somehow alive, tuning itself toward consciousness. Others find solace in the multiverse, where our universe's perfection is just a statistical inevitability in an infinite sea of failed attempts. But no matter where you land, the constants force a reckoning. What does it mean to live in a reality that seems against all odds made for us? Then there's the sheer existential weight of it all. If the universe weren't fine-tuned, we wouldn't be here to notice. That circularity is either profoundly comforting or unsettling, depending on how you look at it. It's like waking up to find yourself in a locked room with a single, intricately crafted key in your hand. Was the room built for you, or did you just happen to stumble into the one room where the key fits? The answer shapes everything, from our sense of purpose to how we treat this improbable oasis we call home. For scientists, it's a call to dig deeper, to hunt for the hidden laws that might explain the numbers. For philosophers, it's a reminder that reality might be stranger than any story we've dared to tell. And what if it's all just luck? The thought can be liberating or lonely, depending on your temperament. If we're here by chance, every moment becomes a kind of miracle, a fleeting spark in an indifferent cosmos. But it also raises the stakes. In a universe without guarantees, our choices matter more. The fragile balance that allows life isn't just a backdrop. It's an invitation to pay attention, to cherish the conditions that let us exist at all. That's the paradox of fine-tuning. Whether you see it as destiny or dice rolls, it leaves you with a question that's as old as humanity itself. Are we the universe's way of understanding itself, or just a happy accident in the dark? The answer, like the constants themselves, might be beyond our grasp, but the asking changes us all the same. The fine-tuning of the universe's constants isn't just a scientific curiosity, it's a mirror reflecting the deepest questions about reality itself. Every time we measure the speed of light, calculate the strength of gravity, or ponder the mass of an electron, we're staring at numbers that shouldn't work together, yet somehow do with breathtaking precision. It's like discovering the combination to a cosmic lock, only to realize the dials were set ages before we even existed. And that's what makes this mystery so electrifying. It's not just about how the universe works, but why it works this particular way. Some see the multiverse as the ultimate answer, a vast, bubbling froth of realities where every possible combination of constants plays out. In most, the numbers don't add up, and existence flickers out before it can begin. But in a rare few, like ours, the conditions align just right, and life emerges to marvel at its own improbability. It's a compelling vision, one that turns fine-tuning from a miracle into a statistical inevitability. Yet even this explanation leaves a lingering question. Why does this universe feel so exquisitely arranged? If there are infinite worlds, shouldn't ours feel more like a rough draft than a masterpiece? Others believe the answer lies hidden in physics we haven't yet uncovered. Maybe the constants aren't arbitrary at all, but bound together by a deeper symmetry, like notes in a chord we can't yet hear. String theory whispers of hidden dimensions where geometry dictates the values we observe, while quantum gravity hints at laws that transcend space and time. These ideas are still in their infancy, but they share a tantalizing promise. The universe's precision might not be accidental, but inevitable. Then there's the humbling possibility that we're asking the wrong questions entirely. What if fine-tuning isn't a problem to solve, but a clue that our understanding of reality is still childlike? Centuries ago, lightning was the wrath of gods. Today, it's a dance of electrons. Could the constants be the same, a mystery that only seems mystical until we find the right lens? Whatever the truth, one thing's certain: the universe didn't have to be this way. It could have been chaotic, barren, or stillborn. Instead, it's a place where atoms dance into galaxies, stars forge the elements of life, and consciousness arises to ponder it all. That's not just a lucky break, it's an invitation. An invitation to keep digging, to stay curious, and to embrace the wonder of not knowing. Because the greatest discoveries often begin with the simplest question: what if? So as we close this chapter, remember, the cosmos isn't finished revealing its secrets. Every equation, every telescope, every daring idea brings us closer to understanding our place in this vast, improbable tapestry. And that's the real magic of fine-tuning. It's not just about the universe's design, but about our endless quest to unravel it. The story's far from over. Let's keep writing it